Now let's have a look at the first makefile example. This is the most rudimentary example that we just saw in the slides. Now here, targets and prerequisites have been mentioned only in this line. That is the build example outline. Prerequisites have not been mentioned in the previous commands. As you can see here, no prerequisites have been mentioned, and we have a final target as build example bin. So there is a lot to learn from here. The targets are not file names like we saw in the slide. So the targets are not file names. Here the prerequisites are not file names. So how would this makefile behave? But even then, it follows the basic characteristics of make. So, and one more thing, if you have to run this makefile, there is no all target here. So for example, we do generally when you do a make, you'll do a make all and everything will be compiled. Here we don't even have an all. Okay. So I purposely done that to show you what is the behavior of make if the all is not there. So suppose you just run a make on this file first. So what happens? So here is the file, and this is the make, and since it's a separate file name, we have to give make a -f makefile without prerequisites and target names. And if you run this, you'll see that it only runs the first line, that is the first command, and it stops because it really does not know which target to execute. So by default, it executes the first target and then it stops. How do we force the makefile to actually create a target? In this case, what do we do? So what we'll have to do is to ask make to build the final target. So we know that the final target is this build example bin, that is the binary, right? So if we ask it to run this final target, then it will start checking the dependencies and it will build everything. If we ask it to run this one, then it will only check these prerequisites and only build up to here. I hope you're getting it. So now if we do make -f makefile without prerequisites and bare target names, and then give build underscore example underscore bin. So underscore as you can see, it runs the whole set. So you will find that the binary file has been created here. So now if we run up, so let's do a clean. I have at least the clean part created here. So the binary files and everything vanishes here. So whatever has been built vanishes. So now let's do one thing. Let us try to just run up to build example.out, that is up to this target, and see how the make behaves. So let us run that. So instead of build example bin, we do build example.out. Okay. So now you will see it has only created the object files, but it will not have created the bin. So all the object files have been created. .out file has been created, of course, but then the binary is missing. So do you understand how the make is checking for dependencies here? It is whatever stage you ask it to make, it checks the dependencies for that stage and only prepares the output for that stage. It does not come here because the dependency tree that time only takes these three into account, and it is not necessary that these have to be on top. It can be anywhere. It can be anywhere in the makefile and it will still build the dependency tree. We have just put it like this for our convenience, but this could be anywhere. So dependency tree keeps getting added to as the make process progresses through the makefile. Okay, so there is no hard and fast rule about the order of what you place here, as long as you put the dependencies properly. Now let's do something. Let's change one of these names. So even though it's not a file name, let's change the target name into build name main underscore say xxxx. So what happens is, now there is a target name here which does not have a rule, because this target does not match with anything that make can find. So there are two things make does at this point. One is it checks for the targets in the make file, and second is if it cannot find it, then it will look for a file by the name of this. Okay, so it will check for the targets, and if it is not found, then it will look for a file with the name of this. And if it still cannot find the target, then it will abort. So when you run the make with the changed target name, you'll see that make is throwing an error saying there's no rule to make target build example main xxxx needed by build example.out. So it stops. By any chance, if it found a file of this name, it would go ahead with the make process. Okay, so if you want these prerequisites to be dependent on these targets, then make sure that the targets are unique and there is no duplicate file existing with the name of these prerequisites. So this is what is going to happen if you change the name of the target. So let's change it back, save it, and if you run it again, the make process goes through. I hope you understand what is going on here. Because of the dependencies, so the make file is checking the dependencies in this way. For example, so make sure that say build example.main, like I said, if you have a prerequisite here like this, make sure that it does not have a duplicate file name. For example, when you say build example main, so you have a target build example main. And you also have a file with the same name somewhere, then it could be a problem. Okay, for example, you have a file name like we changed it to build example main underscore xxxx, then it's going to be a problem. It will still think that if it is not able to find the target here, it will look for the file and it will go ahead with the build process. Let's check that out as well. Okay, let's create a file with name build example main underscore main xxxx and see what happens. So previously we saw that the make process didn't go through. So now let's create a file. So let's create a blank file and check what happens. So build example main okay, so this is a blank file, build example main xxxx. Now what we are going to do is we will open this one and rename it as xxxx. We'll save it and we'll try to run the make process now, and we'll see what happens. Previously, as we saw, the make process failed, right? So let's see what happens now. So when we do the make again, as you can see, it ran the process because it found this file in that particular directory. So it ran the process thinking that particular file exists. It doesn't matter if this target is not related to any of these targets. If it finds the file, it will run it. So let's do one thing. Let us delete that file now, build example main. So and see what happens now. So we delete the file. After we delete the file, let's try to run the make again. Deleting the file again, it will give an error. So let us run it and we see the no rule to make target error come up again, because we deleted that file, that is build example main xxxx from here. Okay, so this is one way make checks for dependencies. Now this is the most, as we said, this is the most rudimentary makefile that we can write. Now what are the disadvantages of this? We saw that it does the dependency check correctly, even in this case. But what are the drawbacks of this particular way of writing the makefile? So let's suppose now we make some changes to the build example main. Say suppose, let's change this back. Let's say we make some change to the build example main now. Ideally, make is supposed to keep track of the timestamp for the particular prerequisites, right? So let's say we have build example main opened here. So say this is build example main. We will not do anything, we'll not do much. We'll just say, let's comment this out. Okay, let's comment this out and save it. Now when we comment it out and save it, what make ideally is supposed to do is, in this case it will not happen. What make ideally is supposed to do, which we shall see in the third third iteration of this makefile we will write here. Even if we change this, ideally make is only supposed to that particular command. So if we have updated the main, it will only do a version check for the main, run this particular target, run this particular rule, and it will, after it runs this rule, it knows that it has to build the binary again. It is intelligent enough to know that, and then it builds the binary. It leaves out a few steps in the middle because those are already built. But in this case, if you see, that will not be the case. In this case, it will again repeat the whole process. So even if we just made a change to build example.main, say, it just repeated the whole make process. We don't want that, and the reason we don't want that is this is a small makefile and a small project. Now suppose it's a huge project with a lot of compilation to be done. In that scenario, if make reruns every time we make a small change, that's a huge loss of time and effort. So we have to write the makefile in such a way that we can save that time and effort and make only touches what is updated, and then does the final creation of binary. We shall see that shortly. So this is the first iteration of make. Okay. Even similarly, even if we did something on this side with the target files, make will be non-responsive and it will build the whole thing again. So this particular version of the makefile, the most basic one, only checks for dependencies between the targets. It does not check for the timestamp of the files because we have not written the makefile accordingly. So it's not make's fault. This is a, you can say this is a very primitive way of writing make. In the second iteration, all we have changed in the makefile is that we have named the targets as the output file names. For example, core initialization stm32 stm32f4 11xc.o build example main.o. So the targets follow the file names startup gcc.o, build example main.out, and build example.binary. Okay. The right hand side is the same. We have not made any changes. Only change that we have made here is we had to make this prerequisite as a file name because it has to find that target, and of course, and here also we have to name the prerequisites as file names because it has to find out those targets, right? So since they are named, they have file names now these prerequisites will be file names. So let us see what advantages we have of this makefile over the previous one. So let's Again, we'll do the same thing, but now it'll change. So make file without prerequisites and bare target names. This is make file without prerequisites and so long names. So it is make file without prerequisites and target names as file names. So make file without prerequisites and target names. So now we will try to run a make on the next iteration, and I have purposely named this one wrong. That is the target name wrong here. So it should be build example.bin. We have made it build example underscore bin here. Now let's see what make has to say. So make says that no rule to make target build example bin. So it is not here. As you can see, build example bin is not here. So if we change it to build example.bin, it says build example.bin is up to date. That is, it has detected that build example.bin is already there and no changes have been made to build example.bin since the last time make file ran. So can you see now, make in the second iteration, make has already started making keeping track of the versions of these files, the targets at least. So let us change, or let us delete the bin file now. So if we delete the bin file, now we could see, as far as the output is concerned, so you've only named the targets as to their respective file names. Now the problem here is we cannot open the object file and make some changes to it. I don't want to do it. So the maximum change that we can do to the object files or the output files is delete the files so that we can and see the behavior of make. So now the bin file is gone. When the bin file is gone, let's see what it does. Did you see that? It did not run anything else. It just ran the obj copy command. So this is the beauty of make, which plain scripting would not do. It just ran the obj copy command because it knows that the previous stages are all ready here. So all the .o files, everything is ready. So why run them again? Let's just run the obj copy, which will create just the bin file. So you see the beauty of make now. What it's doing here is, I just deleted the build example.bin, but from the previous run, these object files already exist. So make did not touch those object files. It says that, okay, since last time I ran the make process, all these object files are already existing. So why should I run it again? It just runs this and creates the bin file. Now let us delete the core initialization object file and see how make behaves. So let's delete the core initialization object file now. So let's find it. So this is the core initialization file that we have. Let's delete this file. So once we delete this file, now the core initialization file is absent. The bin file is present. Okay. The core initialization file is absent. The bin file is present. Let's see what make does now. So let's clear this up, and we have. So this is the situation now. So, and we'll just try to do a bin again. Now, ideally, what make should see is the core initialization file object file is gone. So it has to rebuild the object file. If it has to rebuild the object file, then it has to rebuild the bin. So ideally, it should run, and it should run the linker also. Okay, because that file has been. Let's see what it does. So it didn't run everything. So what it ran? It first built the core initialization. Then it ran the linker because it has to be linked with the files, and then it created the bin file all over again because it's a new object file now. The object file has changed. The two steps that it skipped are startup GCC and the build example main. So it did not build those two object files because it is already existing. Now you see the logic, how make works. Now If we make a change in the, as we said, if you make a change in the startup GCC like we did, it will not just rebuild the startup GCC because it does not know yet what the, we have not put the .c files in the prerequisites. So I made the change here, but I did not show you. So let's uncomment this again. So this will be considered as a change. And let's do a Control S. Now, what basically happens is, let's comment this line out now. Okay. So what basically now happens is this file has changed. Now, if we run the make process again, it says it's up to date. It says it is up to date because we are not asking make to check the version of the input files or the input C files. If we had asked make to check the version of the input.c files, then it would actually run this process again. That is, it will build the build example main file again because it has changed. So right now that is not happening. So in the second iteration, what do we see? We have the, it is doing a version control, of course, or it is doing a timestamp control of the .bin file because these are file names. If one of these .out files are being deleted, it is actually rebuilding that particular rule, and then it is doing the link, and then it is creating the binary. All of that it is doing, but it is not keeping track of the versions of the input files, and it is not keeping track of the versions because we have not asked it to keep it track of the version, because we are not putting anything as a prerequisites here. So if we put the input files as prerequisites here, it will do that as well. That is, it will keep track of the input files as well. So that is our third iteration. That is where we check for the versions of the input files as well. So let's do that. So the third one is make file with prerequisite and target names as file names. So it has prerequisites and it has target names as file names. Okay. So this file differs from the previous file because we have also added the prerequisites. We have a .c file here. We have the respective .c file here, and so on. Here the .o files are already there from the prerequisites that we saw previously. And then we have the, and if you observe, we have also included the header files here. Okay, that is in the build example.out. Okay, we have included the core initialization header file. We have included the memory map header file. Okay. So what happens even if the header files change and we ask it to do a build example.out, it will also check for the header file. We shall see that. So now how does it behave? Let us try to run this now. The name is make file with prerequisites and target names as file names. So this is more or less a more complete version of Makefile, though this is also rudimentary because for the next iteration, that is the final iteration, we will actually build a Makefile the way it should be built. So which will save us a lot of effort in, for example, here in this case, if you want to add a file or drop a file, you have to individually go to the rules and you have to change the file names and everything. All of that can be parameterized, and the Makefile may be looking a bit more cryptic, but even in the long run, it is much more beneficial for you. But nonetheless, these Makefiles are going to give you a good idea about how Makefile behaves. So now let's try to build this. So make without prerequisites. So it is Makefile with prerequisites now. Okay. So the name changes, and let's try to build it. Okay. So now it builds the binary. Now it built the binary, and what did it build? It built the build example main.o, as you can see. It build example main.o, and then it loaded and it ran the linker. Okay, can you see this? This it did because we had edited that particular file. And what was the command? We asked for it to do build example.binary. Now let's change it again and see, because I feel that it is not doing something it should do, because the build example binary, it should have rebuilt the binary file, but it is not rebuilding the binary file. So let us see where the problem is. So let's have a look into the make file. So we made a change here. We made a change here in build example main.c. Okay. So now let's try and change the build example main.c file once again. So I've not made any changes to this file. We'll just try that out once again and see if it picks up the change. So now let's uncomment this and save it. So that's a change. And let's try to run the make once again. Clean this up. And so we are trying to do build example.bin, and what has changed? Only the build example main.c file has changed. Nothing else has changed. But then if that C file has changed, what needs to be done? The make has to rebuild that .c file. If it rebuilds the .c file, then it has to run the linker process again. If it has to run the linker process again, it has to build the binary again. So let's see if it does that. So it has rebuilt the build example main.c file because it was absent. It has run the linker again, and it has created the binary again, as you can see. So it is working. This is how this third iteration works. So we have the make file with the prerequisites as file name. So now let us try to change a header file and see if it works. So let's now. So if we change the header file here, since the header file is only in the .out phase, it should rerun the .out rule only. So it will not do anything much. In fact, frankly speaking, if you really want the header files to be picked up in the right places, you should have mentioned them here. The respective header files should have been mentioned here. It will not. So whatever we have done is incorrect in a way, because if we have mentioned the header file in the out stage, if we just change the header file, it will just run this step once again, and running this step once again does not really pull in the necessary header file changes. So whatever make file I have shown you. Okay, even though the header files are mentioned here, it will run the .out stage maybe once again, but the header changes will not come in because the files have already been built in this stage. Okay, it will not go up to here, it will just run this. So let's check that. Let's make a change to the header file now. Let's go and take this header file and let's create a few spaces here. So this has changed the header file. Now if we run make again, see what it does. It just runs the linker and it just creates a binary. Can you see that? Because I have added the header file information in this stage. Now this only creates the .out file again. It does not, the header file changes really do not go into the files. Okay, it just sees that the header files have changed and it reruns it at this stage. That is the .o stage where these files have already been built. So your header files need to be written here and not here. So this is take it as an assignment and fix this make file in such a way that when you change the respective header files, those changes actually go into the object file. Okay, so do that, and then if the respective header files are mentioned in these places, will you see that the make file process is picking up the changes in the headers as well. This here it will pick up the changes in the header, but the header files changes will really not go into the make file as such. If you made some changes to the header file and did a make clean, of course, then the new header files will be pulled in, right? Because that time everything is fresh. So you make a change to the header file and then you do a make clean change to the and change the header file, then the whole process is going to repeat that time. So let's do a make clean. So let's change our header file now. So let's just delete these spaces now again. So this is equivalent to changing the header file, and let's do a make clean. So if you do a make clean now, again, if you run this, okay, let's not run this because again we'll lose the change. So let's do a make clean here. Now the header file is changed. Okay, we have not run anything. The header file is changed. Now we do a make clean, and now if we do a run, it will run the entire build right across from the first file to the last one. It will run all the steps. It will run all the rules. Okay, because it's clean. It doesn't find any target and it has to build everything from the scratch. Make files are language agnostic, as long as these shell scripts can be for building any language actually, for that matter. Okay, so it's not only for C. Let us see some errors. So we saw some errors in Makefile. So now here, this is a prerequisite. Even though it's a prerequisite, this prerequisite is not mentioned as any target, of course, right? Because this is the base file. But then, as we discussed, make is looking for this file name actually at that point. If you mention a prerequisite and that prerequisite exists as a file name, then it takes it up as a file, and then it allows that particular rule to run. Okay, so that is how make takes care. If this was a target name somewhere, then it would have gone to that target and fetch that rule, and it would have run it. So whenever so say there is you are doing a make and you get an error saying no rule. This is one of the most frequent error that you get, no rule to make target. This either means that there is such a target name does not exist in the make file, or whatever target it is looking, whatever prerequisites it is looking for does not exist even as a file name anywhere. These are the possibilities under which the make file is going to throw an error. So what you need to do is you need to check if the prerequisites match up with your targets, and or if you are just compiling a basic C file, and you have to check whether this C file name matches with the file that already exists. Otherwise it will not work. And in the first iteration we saw that you need not even put prerequisites, but in that case the make process will not check for your timestamps. Okay, and if you need it to check for timestamps, then this is how you write the make file. So the next iteration is going to be the final make file. That's the completed make file and how it looks. Now this is the final make file, and it looks very different from the three previous iterations, and we have gone through the make file in the presentation also, but then we will also have a look at the make file script. We talked about all of this. We talked about the variables and we talked about the prerequisites and everything for this particular make file, but it looks much more concise and it looks much more cryptic, and we have actually gone through all these symbols and what they stand for, and it exactly does what the last iteration, that is the third iteration we saw, does, and it does much more. That is, it searches for the path for your C and header files. It does a lot more things. But here again, for this particular make file, okay, since the header file information is here, that is, this make file logic is different, as we saw, because slightly the commands that we wrote are slightly different, as you remember. So here let us change the header file and see what it does. Okay. So in the previous make file we mentioned that the header file was change was not getting picked up by the respective C file, right? But here let us change the header file and see what happens. So we'll just create some spaces here and see what it does. So now in this case it's just a plain make file. So we can just run make all. So when we do a make all, let's see what it did. So as you can see, it ran the entire GCC command with all the 3 files here. And then it did a linker example.bin and it created the binary file. Okay. So it did a armrun UBI GCC and it ran the whole process. -i include startup gcc.c and code initialization.c, build example main.c. So here the make file is written differently. So even if you change the header file, the entire process is getting run once again, because it is not done in stages. It is all getting into the final make file. So let us make a change in one of the C files and see what it does. Build example main.c. Let's comment this out. Okay, and see how this make file runs. So let's do a make all. And if you see, it is running everything. So source and build and everything. So this make file does a version check. It definitely does a version check for you. But then this make file is one disadvantage we see of this make file is, even though it is much more concise and you can add the files and delete the files separately in a different place in the file. That is, you don't need to go down and make changes here, since this is just one rule here. Okay, every time any file changes, every time any source changes, the entire rule runs. You see that? So version control is done here. Version control is done properly here, but one thing that is not done is it does not make the build process shorter, and that is because, like we saw here, the build process was split up into different steps. Okay. In this case, the build process is not split up into steps. It is all together. So if you make any changes in any of the .c or .h files, you will see that the effect is of compiling everything together. But yes, the only advantage of this file is it is much more easy to handle, because say you need to put a new C file in your project, or you need to change the names of any of these C files, you can just change it here in the sources and it will be pulled in here. Or you want to add a header file, you want to add a new C file, anything you do, you can just do it in these two places and the change will trickle down here without you having to do anything here. These are highly parameterized. But then again, the problem here is it is going to run the entire build process over and over, even if you change one file. The advantage of this was not parameterized, but if you made any change to that particular stage, it only ran that stage, which is not the case here. But these at least these prerequisites, these iterations helped you to understand how makefiles behave. So I think after going through this segment of the course, you should not have any doubt about how makefiles work, and work on these makefiles and make changes. If you get a lot of errors, because that is how you will learn. And keep me posted about how your progress is. Let me know if you need any help. I'm always there to help you out. So we see the target called all here, which is declared as a phony target. Now we talked about phony targets. So here you would see that if you have dealt with makefiles before, there is a very common command given as make all. Another command is make clean. Now this is how make all is incorporated. So basically all has the prerequisite is the output binary, and all is a phony target. So even if there is a file called all, it will not check for the timestamp. It will run it nevertheless. So every time you do make all, this statement is executed. It will, because all is, if there is a file called all and it's updated, make is not going to wait. Make is not going to just skip this step. Okay. So generally what happens is when you do a make all, the output. So it sees the prerequisite as the output binary. It checks for the prerequisite. It goes here. Then it sees that the prerequisite is the output object. Then it checks for the output object here, and then it actually does the entire compile here. So the code is compiled, and you have obtained all your object files at this stage. Okay, and then it comes here. So we discussed about this. So it comes here. So it's resolving the dependencies. It comes here, and then here it creates the binary, okay, or the .bin file at this stage. So we know that the obj copy command is, so by just issuing this command, it is performing all these actions. It has come to this part of the tree, dependency tree. That is say, you can say it is one of the leaves, you can say, of the tree, and then it resolves this. Then it uses the output of this to resolve the output binary, and then it goes to make all. Now make all does not have anything to resolve. It just invokes the entire process. That's all. Okay. So this is why you could have also done make and output binary. Okay. You could have done that as well, and make would anyway have run. But then, so whatever is the output binary file name, you could have just given that name, and make would anyway have run. But make all makes it, you need not know the name of the output binary, right? So make all is going to take care of it. So make all, that is how make all works. And maintain this convention absolutely, because we will be, as we saw, we are running, we are doing, since this is a bare metal course, we are directly running Makefile projects in CubeIDE. So since we are running in CubeIDE, this all has to be there, and make clean has to be there, because CubeIDE understands these two keywords. And make clean similarly it's again a phony target, and it does not have any prerequisite. So when you run clean, it just runs this command. It doesn't look for any dependencies. It just comes and runs this command. And since clean is a phony target, it doesn't look for any files with the name clean and checks for its timestamp. Okay. So that is something you have to be careful about. So mention the all and mention the clean in your Makefile whenever you create them. Besides the ELF file format that we studied, there are many other file formats that are used. So in our case, we just did the ELF file format, but for your information, there are file formats like OS360 and VS9 mainframe and VS9 for mainframe operating systems. You have GOFF for IBM MBS and ZOS, A.out, which is Unix-like, okay, COF, which is Unix-like. So these are file formats like ELF. So they will again have their files are going to have different. Their layout is going to be slightly different from ELF, but mostly similar. Then you have ECOF, XCOF. Then we have our ELF, okay, Mach-O, SOM, Amiga, Hunk, PEF, CMD, and so on. So this is the Wikipedia page for comparison of executable file formats. So you can just go there and just have a look. Now this is also for your information. So when you are running this Makefile, when we are running our Makefile projects in CubeIDE, the CubeIDE does not, though we are creating the binary here, that is our output binary, whatever binary file name we give it, CubeIDE does not need that binary file name. All CubeIDE needs is the name of the output.out file or whatever. So you need to mention the name of the .out file to CubeIDE. Okay, that is for debug. So in the debug configuration, just mention the name of the .out file. So what it does is it will create the .bin file out of this .out file. So whatever, if you name the .bin file to something else here, it disregards it. It does not use this bin file. Instead, it uses its own bin file. That is, from the out file, it runs its own obj copy command internally and creates a bin file which it flashes on the board. Okay. But in case, so in this chapter we have manually, or we have used commands, make file commands, or we have used make commands, we have used linker commands, we have used obj dump, obj copy. So in case you do not want to use the cube ID and you want to flash your own binary image onto the board, keeping the cube ID out of the equation, that was also possible. We can use the STM32 programmer for that. So you can directly flash your binary onto the board. That is the binary that this makefile creates by itself. So we'll just have a look at the ID to show you what we mentioned here, that is mentioning the name of the .out file and how cube ID converts that .out into the .binary that internally and does not use this. So we spoke about cube ID not requiring the binary file that we create with our in our makefile, right? So we'll try that out. So this is something we saw, that is, when you do a make all, it tries to create the output binary and then it goes down the dependency. When we created this particular project, if you go to the debug configuration, you will see that the C++ application name is buildexample.out. So our makefile has to create the buildexample.out. If you name it as something else, then the make process is going to fail. For example, if you name it as here output object, if you make it buildexample1.out, okay, the cube ID is going to look for buildexample.out and it is going to fail here. So let's clean up the project. So when you do a clean and then you try to do a run, you'll see an error coming up here. That is, if you look into the details, it says program file does not exist. That is buildexample.out not found, because the process ran and what it created is, if you look in the binary, it has created buildexample1.out, and we have instructed cube ID to look for buildexample.out. Okay, so this is one thing that you have to keep in mind. So this name has to be the same. So what we do is we revert it back to buildexample.out. So when you do that, you save it and you run it once again. Now it will be able to flash the image on the board. So it is creating the binary from the out file. Now, how can you be sure that is creating the binary from the out file and it is not taking the binary that we have made? So the binary that we have made is here, that is linkerexample.bin. Can you see this? It is linkerexample.bin. So in the makefile, we have just changed the name for our binary file, this one. Okay. So it has created the linkerexample.bin, but it is not using that. That is, cube ID is not using it. How do you know? How can we be sure about that? We'll just skip this step. So in the all, instead of output binary, we'll just put output object. Okay. So if you put output object here, it will skip the output binary step, obviously, because it is looking for the dependency here. So the dependency is going to be satisfied by this rule. It is going to skip this rule completely. So we'll see that here the output binary, the linker file that we were talking about, linkerexample.bin, is not going to be created. Okay. But even though it is not created, we'll see that the image is still flashed to the board. Now that is only possible because, so if you do a clean, let's clean it up. So the binary is not there. Okay. The makefile is skipping the binary creation, and we'll see that that linker, this binary build linker example.bin is not going to be created. Even though it is not created, we'll see that this is still going into debug. That is, it is flashing the image and it is going into debug mode. See, download verified successfully. So it is still downloading the image. We have not created any binary file. If you can see, the our.bin file is not created because we are just skipping that particular step here. So CubeIDE only needs to know the name of the object file and not this one. Okay. So that is something that you have to keep in mind. Right. So it still flashes the code and it goes into the debug. And you know a little bit about the makefile here also. That is, this is how the dependencies work when we have not created the binary. Now, what if you don't want to use the CubeIDE and you want to flash the binary image onto the board? We spoke of the QProgrammer in that case. So we can flash the image. So at that point, what we are going to do is we are going to we'll move to a different code base, not this one, but nevertheless the logic is the same. That is, we will be creating a binary file and we will flash the binary file, but we will not use CubeIDE in that case. Let's revert it because I might forget it later. That is to put the output binary, because the output binary is anyway necessary for us. Just that if we are doing it through CubeIDE, it only needs the object file. So it is internally creating the binary and flashing it on the board. That is, it is running an obj copy command, probably internally. It is not using this step at all. So let's now go to the makefile chapter. Or makefile segment, as I like to call it, and open a prompt there. So this is our makefile. And let us open the makefile. Is already opened in Notepad QQ. So this is the alternative to Notepad++ on Windows. So you have this makefile and we have make all, and it is creating the binary and everything. So see, the binary that we are creating is linker example.bin. That is the binary file name. So if we do a make all here, it is going to create so because the binary is existing, so let's do a make clean and then again do a make all. So it has created the binary. Let us go into the folder and check to be sure whether the binary is created or not. So here is the binary created. Okay, Thursday is the date. So it has created the binary. Now, without using the CubeIDE, we'll flash the binary, and we need to do it when you are in the makefile linker chapter. I would insist that every time you create a binary, you try out your makefile iterations, makefile iteration 1, 2, 3, 4, whatever binary is created, try to flash it on the board and see if the code is working. So then that will give you confidence that your makefile linker indeed works. If you use your makefile and linker for some reason, if there is some error with your linker file, and then if you flash it on the board and you see that the LED is not glowing or something is not happening, then it means there's some problem with your configuration. So that is something that you need to keep in mind. And in such cases, if you want to run the binary file that you have created, because as you saw, CubeIDE is not using your binary file. using your obj copy command, then you can use the, so let's close the IDE here. We'll close the IDE here, and what we'll do is we'll open up the Cube Programmer. Once the Cube Programmer is open, ensure that the board is properly connected to your workstation. Click on the connect button. So your programmer is connected, and it will immediately start showing you the code that is actually there on your board, that is 200000408 and so on. So this is the exception vector table. If you go down, you'll see you'll see the opcodes and everything. Okay, so this is the dump of the code that you see here. So we are more interested in burning the binary on the board, and the starting address is, as we know, is this 8 with 6 zeros. So we'll do a verify programming, and we'll not skip flash erase. Let it do a flash erase. So let us browse and make file linker, code examples for demo, and build example.bin. So it is not build example.bin. So if you click this now, it is going to fail. So what is the name of the file? Let's check up the make file. So we have given the name as linker_example.bin. So let us, instead of build, let us make it linker_example.bin, and then do start programming. So it says it doesn't exist, and we have linker_example.bin. Open this, start programming. So download verified successfully. So your file download is completed. So it's pretty straightforward. It's quite simple. So if you again have a look at the memory map, you can see the memory there. And if you want to erase the flash, you can do full chip erase, and then you can do just erase the complete flash this way. So now the board is blank. There is no code on the board, and then you can again do a start programming, and it is going to write the program or burn an image on your microcontroller. So this is the STM32 Cube Programmer that you can use to program. So use it in your Makefile linker chapter. So since we are learning bare metal programming, and I repeat, the beauty of the bare metal programming and the way we have approached this course is that as you saw, we can use this same piece of code, and we can put it in debug in the Cube IDE, and the Cube IDE is going to debug it without any complaints. So you can put the code on debug and check everything, and it's the same code that you can make on a terminal, okay, and burn it onto your board even without the Cube IDE being involved. So I personally feel that it's the best of both worlds. We get to learn linker makefile also, but of course we are not using the other features of Cube IDE like code generation and so on. So ST allows you to actually choose your architecture and configure your pins and set up your drivers all automatically. But that was not the intention of this course. The intention of this course was to learn everything the hard way. So that's the reason we have stayed away from automatic code generation. We have done whatever we have done here, we have done from the ground up. So and that was the intention of this particular course.